Thank you very much, Alexander. And let me first start thanking you, all the organizers, for giving me the opportunity to explain my work and the work of my lab here in this nice conference. And yes, I'm going to dedicate these 15 minutes to explain you my work and try to convince you that a new point of view, the point of view of complexity theory, can be useful for the origin of life and disciplines related to it. Okay, let me first start with a few sketches, a few lines of the main difficulties that we have associated with the origin of life for the last 100 years. The first one is that we know very little about early Earth life and environment. You all know this, I know, and many of you know this much better than I do. There is no fossil record before the last universal common ancestor, and there will be never. We do not know the physicochemical and environmental characteristics of the early Earth, and this is critical. We don't know the salinity of the sea. We don't know its pH. We don't know the temperature of the atmosphere 4,000 million years ago. I'm not a chemist, I'm a physicist, but chemists always say, hey, Jacobo, you don't know how dependent chemistry is on the environment. And so this is really a complex situation because we cannot do thousands and thousands of experiments. So this is a big barrier. Not only that, we didn't have any other models, any other life models to compare with. We know of no life so far beyond our atmosphere. We're looking for it on Mars and in other places of the solar system, but the truth is that actually we haven't found anything yet. And articles like this one that was published by people in my center, in my institute a few months ago, say that our detection limits are still a bit too low. So we might still have trouble finding life in Mars, for example, even if it's there. But I'm sure that in a couple of decades, this problem will be solved. But still, there are lots of difficulties. And well, by the way, we already had some false positives, like this strange fossil that was a geological structure in a meteorite. So you have to be very careful when we look for life out of the Earth. Not only this, we could say, okay, let's forget about life out of the Earth. Let's try to understand current biochemistry to get a model of what could have happened in the origin of life. Well, you all know that current biochemistry does not help us very much. Real biochemistry, actual cell biochemistry, quickly creates very, very complex and very efficient molecules that help the cell to get divided, and to grow. But in the origin of life, we definitely need to find something much simpler, much more inefficient, probably, and much slower than the processes that we are having now in current life. But not everything is bad, because 3,800 million years ago, more or less, we had a lot of time, between 100 and 300 million years. We had many parallel attempts to create life, and we had, and this is very, very important, and actually Darwin was actually aware of this detail, we had a lifeless world. So if life appeared now again, other types of life would eat it and would destroy it very fast. But in the early Earth, there was no competition, and this is very good news. So what do we propose? In the last 10-15 years, apart from all these classical approaches from chemistry, from biology, and from geology, there is a new line that proposes a systemic approach. That is a change of perspective. So let's go from the particular, the more reductionist, to the collective. Collective systems. Why complex systems or why collective systems? Because a complex system is a system that is composed of interacting elements that present emergent global properties. And this is very important. And because these global properties cannot be predicted just by analyzing its components individually. And so what we propose is to look at this origin of life from a more general point of view. This is what some chemists call systems chemistry, or some biologists systems biology, if you want. This is more or less the philosophy. But from physics, we call it complexity theory. And so with this aim, I created, like 3 or 4 years ago at the Center for Astrobiology in Madrid, the Complexity and Astrobiology group, where our main objective is to build a bridge from complexity theory to astrobiology. And our tools are numerical and are theoretical. We don't do experiments, but we collaborate with experimentalists. Complex networks, game theory, mathematical and numerical modeling, also data science, Bayesian statistics, artificial intelligence, all those kind of tools is what we use. And so, well, this is our general objective, but our specific objective is to study the increase of complexity in different steps that have gone from the creation of the first molecular bricks of life, probably in a molecular cloud 4,000 million years ago, even less, even before, until the current biosphere. So we want to, if you want, we want to go up this complexity ladder in different steps. And so now I'm going to sketch very briefly 4 or 5 lines that we are developing. Some of them are already finished. And what we have been doing is to study different moments, important moments of this long way from astrochemistry to prebiotic chemistry, and from prebiotic chemistry to current biochemistry in different moments. So in this, if you can look at this table here, if you go from up to down, the agents that are important are more and more complex, from atoms to simple molecules, from simple molecules to polymers. And if you go from the left to the right, you go from astrochemistry to prebiotic chemistry, and then to current life. Let me explain you this first work. This was published last year. And in this first work, what we did is to introduce a computational environment called NetWorld, in which this has nothing to do with chemistry. It's like a chemistry of networks, a very abstract thing, in which we give 10, 20, 50, 100 isolated nodes to the computer, and the computer, with very simple rules, make these nodes, which can resemble atoms, to interact and grow and create different structures. And these structures can also get divided depending on the environment, which is the only parameter. If the environment is very strong, very harsh, these structures break all the time. If it's very smooth, these structures can grow. So in this very simple work, what we obtained is some kind of a transition in which if the environment is smooth enough, 10 or 15 most stable structures that were able to grow in a very, very harsh environment start to interact and give rise to thousands or hundreds of thousands different structures. So this is like a drastic transition towards complexity. Okay, if this is true, that has nothing to do with real chemistry, it was very nice to see that when I arrived to the astrobiological, to the Centro de Astrobiología, the Astrobiology Center, the astrochemists told me, Jacobo, your model explains really well how complexity, molecular complexity, appears in the molecular clouds, because in the molecular clouds they go collapsing, and eventually the dust is able to protect the molecules from the ultraviolet rays, and these 10 or 15 molecules that are very, very stable and very simple start to interact and give rise to 70, 80, or 100 different molecules. The good point is that our model, that has nothing to do with chemistry, was able, as you can see here in C and D, was able to fit quite well, even quantitatively, the real abundance rankings of two different, actually to 4 different molecular clouds. TMC1 and L134N are here. And this had nothing to do with chemistry. But it is true that sometimes very simple models can explain quite well some processes that you can see in the universe. Because, I mean, at the end, these processes are many times not too complex. So this is a good example of how a very abstract work can explain sometimes real data. More or less in the same context, in the context of astrochemistry, we decided to attack the problem of molecular complexity from a different point of view, from a more realistic point of view. And so we decided to approach the chemical evolution of phosphorus in the interstellar medium. You know that phosphorus is very, very important for life. It's ubiquitous in life. And so we took the phosphorus chemical network and studied this network, but not only numerically, as it had been done for all the astrochemists during the last 30 years, but theoretically. We were able to analyze it and solve it mathematically And so with this way, we had a very, very strong, a very powerful tool to understand how the rate coefficients influence these molecules. And what we obtained, applying Bayesian inference, is that there are some, for example, some reactions, like, for example, this one, nitrogen plus PO gives rise to PN plus oxygen, that in this case, the rate coefficient is probably 50 or 100 times smaller than the value that the astrochemists are using. And we were able to get this information just by a theoretical analysis of the system. So now we can go to, and actually we did it to chemists and say, you need to do experiments, or you need to do quantum chemistry to calculate this, in particular, this rate coefficient with much more precision. So this different point of view is also useful for astrochemists that work usually with real data and numerical work. Let me give you, do a big jump and go from astrochemistry to the region of life on Earth. I won't speak a lot about this because there is a poster by Carla Alejandre that will explain this much better than me tomorrow. But the idea is that we have done a model on a primordial non-enzymatic RNA replication in the early Earth. And this is very nice because we have created a powerful numerical tool where we can test, well, numerical and also theoretical tool, where we can test multiple conditions. We can model, I don't know, very strict or very oscillatory environments. We can try different genetic alphabets. We can do many different experiments. As I said before, we cannot do real experiments, not thousands of them, but we can do thousands and millions of numerical experiments, and this is a good tool for that. Another jump. We're also working on protocellular metabolism, and we're trying to do a model where we mix autocatalysis, which we believe should have been basic in the origin of life, cell growth, and compartment division in a mathematical model where we want to focus on kinetics and self-maintenance. Most work so far, most mathematical work so far, or numerical work, has avoided talking about self-maintenance and kinetics, and this is very important. It's not enough to create a model based on chemical reactions of a protocell. You need it to be stable and to be kinetically reasonable, and this is what we're doing here. So we're trying to understand, in particular, how the topology of this chemical network would influence the growth rate of this protocell, suggesting perhaps a scenario where you can have competition, you can have a selection, and eventually some kind of proto-evolution. Finally, I do this last, I know that's really fast, I'm sorry for that, I don't have much time, this fast journey from astrochemistry to current life, explaining that probably this week or next week we will publish this work in which we have studied how viral and host proteins interact during an infection, obviously in the current biosphere. And we have studied 4 different viruses, all of them DNA viruses. We have studied how their co-expression networks interact and how we can get information of which are the strategies that the viruses follow to attack the host, just by studying these networks and how they interact in time, which in fact is the tools are very similar to the ones that we have used in the other moments of this long way till life. Conclusions? Yes, it's true. We're really far away from a complete solution to the origin and early evolution of life, and we may never know exactly how it happened. But still, there are many things that we can find out. It is true that most astrobiologists I have met, they usually say, Jacobo, we will, in the best of cases, we will find, I don't know, 15, 20, 100 different plausible ways to the origin of life, but we probably will not be able to know much more than that. Okay, that's enough. So our question is, how far can we get with systemic work, with this new point of view, in order to boost the discipline? Of course, complementing the rest of more traditional approaches and give a novel perspective to the problem. We don't really know, but in the next 2 or 3 decades, I'm sure that we will find out how far can we get from this more general point of view, of course, complementing all the work that are doing so many other people. Thanks a lot for your attention.